Hello and welcome back. This is going to be our 8th lecture covering chapter 1.3 on complex numbers. So let's get started. First, we're going to talk about imaginary numbers. So we already know there's no real number x such that x squared is equal to -1. We also know that we can't take the square root of -1. We've invented an imaginary number I such that I squared equals -1, and therefore I is equal to the square root of -1. Furthermore, if b is a positive real number, then the square root of -b is equal to I multiplied by the square root of b. So let's go ahead and simplify these four problems by writing them in terms of I. First, the square root of -25. So using this rule here, I know that that's equal to I times the square root of 25. Well, the square root of 25 is just 5. So you can write this as I times 5, but it's more common to see it written as 5I. All right, let's keep going. Square root of -15. This is going to equal I times the square root of 15. And since 15 does not have a square root, it actually is done here. Next, the square root of -9 multiplied by the square root of -25. So this is going to be I times the square root of 9 multiplied by I times the square root of 25. 9 and 25 both have square roots. So this is going to be I times 3 multiplied by I times 5. Now I'm going to multiply these two numbers together. So it's going to be 15 times, and then I times I is just I squared. This is not the simplest form though, since I squared is equal to -1. That means this is equal to 15 times -1, which is just -15. All right, next. The square root of 15 multiplied by the square root of -3. This is going to be equal to I times the square root of 15 multiplied by I times the square root of 3. Now, when we're multiplying square roots, we can multiply under the root. So this is going to be equal to I squared, since we have I times times the square root of 15 times 3, which is 45. Since I squared, again, is equal to -1, this is equal to negative square root of 45. From here, you can even simplify under the square root more, because 45 is equal to 9 times 5. And we care about that because we know that the square root of 9 is equal to 3. So we can make the term under the square root smaller by saying this is equal to negative square root of 9 times 5, which is equal to negative square root of 9 times square root of 5, which is equal to -3 roots of 5. This process here is simplifying under the root. All right, let's move on. Given real numbers a and b, a number written in the form a plus bi is called a complex number. The value a is the real part, and the value b is the imaginary part. And if a equals 0, then 0 plus bi is purely imaginary. Essentially what this is saying is if we have something like 0 plus 7i, right? So that would make this a value 0. This is just equal to 7i, which is purely an imaginary number, not a complex number, because it has no real part. Examples. Identify the real and imaginary parts of the following. So the number with the I is going to be the imaginary part. So here we have a is going to be 2, b is going to be 3. Number 2. Here a is going to equal 5. However, by the definition of a complex number, it has a plus here in the middle, and ours has a minus. That makes our imaginary part be -7 instead of just 7. All right, let's keep going. Write the complex numbers in standard form a plus bi. All right, so this is going to be equal to -6 plus I times the square root of 18, pulling out this -1, square root of -1, divided by 9. Now remember, we can always simplify under a root, so the square root of 18 is going to be equal to the square root of 9 times 2, since 9 times 2 is 18. This is equal to the square root of 9 times the square root of 2, which is equal to 3 roots of 2. So this is now going to be equal to -6 plus, we have this 3 here, so we have 3i roots of 2 divided by 9. It's still not in the form a plus bi. We can still simplify further. So we have -6 over 9 plus 3i roots of 2 over 9. -6 over 9 simplifies to -2/3 plus. And then we can also simplify here the 3 and the 9 to get I roots of 2 over 3. This is now our final answer. Next, number 2. Here we don't have anything to simplify under a square root, so that's kind of nice. We're just going to split up this fraction. So we'll have 3 over 7 minus 8i over 7. And from here, we're actually done. Our a would be 3/7, and our b would be -8 over 7 in this case. All right, let's do the last one. So here we'll have to simplify under our square root again. However, let's go ahead and pull out this I first. So we have I roots of 75 divided by 20. Now remember, 75 is equal to 25 times 3. So that means the square root of 75 must equal the square root of 25 times 3. Well, this is just equal to the square root of 25 multiplied by the square root of 3, which is then 5 roots of 3. So then this is equal to 10 plus 5i roots of 3 divided by 20. On a side note, if you wanted to write it as I times 5 roots of 3, that's not wrong. It's just kind of odd. It's just more common to write the I after the number. Anyways, this is going to be equal to 10 over 20 plus 5i roots of 3 over 20. 10 over 20 simplifies nicely into a half. And then we can also work on this 5 over 20 to get our final answer as 1/2 plus I roots of 3 over 4. Okay, that's it there. All right, now we're going to look at some really fun patterns with I. I is really cool because it repeats forever and ever and ever. So if I is the square root of -1 and I squared is -1, then I cubed is going to be equal to I squared times I, which is the square root of, which is -1 times the square root of -1, which is equal to -I. So I cubed is just -I. I to the 4th is going to equal I squared times I squared, which is -1 times -1, which is 1. If we keep going, we can see I to the 5th. It's just I to the 4th times I. So this is just 1 times the square root of -1, which is just the square root of -1. All right, and then keep going. I to the 6th is just I to the 4th times I squared. I to the 4th is 1. I squared is -1, so this is just equal to -1. I to the 7th is I to the 4th times I to the 3rd, which is equal to 1 times -I, which is -I. And I to the 8th is going to be I to the 4th times I to the 4th, which is equal to 1 times 1, which is 1. So now you'll notice here that the pattern goes root negative 1, negative 1, negative I, 1, and then starts over. Root negative 1, negative 1, negative I, 1. So you can see I is going to equal I to the 5th. I squared is equal to I to the 6th. I cubed is equal to I to the 7th. I to the 4th is equal to I to the 8th. So they cycle essentially in 4 terms. We can use this to solve problems with I that has very long exponents. For example, if I had I to the 21, I know that this is equal I to the 20th times I. Well, I to the 20th, you could simplify that to a bunch of I to the 4ths, right? I believe 5 times, because 4 times 5 is 20. So this is now just equal to 1 times 1 times 1 times 1 times 1 times I, which is I. Therefore, I to the 21 is just equal to I. I generally like to look for the factor of 4. And then you kind of count up from there. So for another example, if we had I to the, let's say 47. Well, I know if I look at numbers less than 47, I know that 44 divided by 4 is equal to 11. So 44 is a factor of 4. So I can separate this into I to the 44 multiplied by I to the 3, since 47 minus 44 is equal to 3. Now I know that this is going to be equal to 1. So that means I to the 47 is just equal to I to the 3, which is negative I. And that's how you can solve these problems of I with really high numbered exponents. We could even do up to 100. Like if I had I to the 102, for example. This is I to the 100 times I to the 2. And we wanted 100 because 100 divided by 4 is equal to 25. So since this one's exponent is a factor of 4, this number is just 1. This is equal to 1 times I squared, which is just I squared, which is negative 1. All right, moving on. Let's talk about now how to add and subtract complex numbers. What you're always going to want to do first is distribute a negative sign. Anytime you see a negative outside of the parentheses, you want to do that first. When you have a plus outside of parentheses, nothing really happens. So then we have negative 2 minus 4i plus 5 plus 2i minus 3 plus 6i by distributing that negative. Next, you want to combine all of the like terms. So I have a negative 2, a 5, and a negative 3. Well, negative 2 plus 5 is 3. Minus 3 is 0. So these actually cancel out, which is very nice. Next, you want to add all of the terms here. So negative 4 plus 2 plus 6. So negative 4 plus 2 is negative 2 plus 6 is 4. Next, with fractions. So let's go ahead and distribute this negative. So we'll get 3 over 4 plus 9 over 5i minus a half minus 2/3 I. And now we'll have to combine these like terms. So let's first do 3/4 minus a half. So remember, we always need to find a least common denominator. So when we're doing 3/4 minus a half, our least common denominator is going to be 4. So 1/2 multiplied by 2 over 2 is going to equal 2 over 4. So that means I'll have 3 over 4 minus 2 over 4, which is 1 over 4. All right, next let's do the imaginary bits. So I want to add 9/5 and negative 2/3. So we want to find the least common denominator for 9/5 and negative 2/3. Well, that's just going to be 5 times 3, which is 15. So then I'll convert my fractions. So 5 times 3 is 15, right? So I'll have 9 times 3 on the top, which is 27, and 5 times 3 on the bottom, which is 15. And then I have negative 2/3, and I'm going to multiply by 5 over 5. So negative 2 times 5 is negative 10, and 3 times 5 is 15. So then I'll have 27 over 15i minus 10 over 15i, which is 17 over 15i. Moving on. Next, let's talk about how to multiply complex numbers. So we'll multiply them the same way as we multiplied stuff like 2 times x plus 1, where we just had 2x plus 2. So first we'll multiply negative 1/2 by 4. So negative 1/2 times 4 is going to be negative 4/2 I. And then negative 1/2 times 6 is negative 6/2. And then we have this I times I here on my last term. So I'll have I squared. So this will simplify because 4 divided by 2 is 2. So I'll have negative 2i. And then 6 divided by 2 is 3. So I have minus 3i squared. And remember from the beginning, I squared is equal to negative 1. So this is just equal to negative 2i minus 3 times negative 1, which is going to be negative 2i plus 3. And then we always want to write our complex numbers in the form a plus bi. So we're actually going to write this as 3 minus 2i for our final answer. Next, this one's a little more complicated. So I like to start with multiplying the first two terms in each of the binomials. So negative 2 times 4 is going to be negative 8. Then I'll have a negative 2 times negative 3i. Negative 2 times negative 3 is positive 6, and then we can't forget that I. 6 times 4 is 24i. And then 6 times negative 3 is going to be negative 18, and then I times I is I squared. So then this is going to be negative 8, and we can add these two together because they both have an I. So 24 plus 6 is 30. And then again, we can convert this negative I squared into negative 1. So this is going to be negative 8 plus 30i plus 18. Lastly, we can combine these two like terms, and 18 minus 8 is 10. So we get 10 plus 30i. All right, moving on. Complex conjugates. These are very important. They're very helpful. So let's first multiply these out. So 3 plus 4i squared is going to equal 3 plus 4i multiplied by 3 plus 4i. Using this method, I'm going to get 9 plus 12i plus 12i plus 16i squared. This is equal to 9 plus 24i plus 16 times negative 1, which is equal to 9 plus 24i minus 16. And 9 minus 16 is going to be negative 7. That's kind of ugly. So squaring a complex number is not pretty, right? So let's try this one, where we have one of them is plus and one of them is minus. So first we'll do 5 times 5, which is 25, minus 10i, plus 10i, and then 2 times 2 is 4, one of them is negative, so I have negative 4i squared. Now this is pretty nice. Negative 10i plus 10i is 0, so those cancel. So we're just going to have 25 minus 4 times negative 1, which is going to equal 25 plus 4, which is 29. And notice here that there is no imaginary part. So these are called complex conjugates. So a plus bi and a minus bi are the complex conjugates. We're interested in them because when you multiply them together, you're left with no imaginary part of your original number. All right, let's do some examples. Our goal is for our result to be in the form of a plus bi. So notice that in the form a plus bi, we do not have an I in the denominator. That's very important. And the problem with these two is there is an I in the denominator. So how do we get rid of it? Well, the general strategy is to multiply by its complex conjugate. So we want to multiply. Now remember, the complex conjugate is going to have the opposite sign. So mine currently is minus, so that means I want the plus. I need both. So since this is 2 minus 7i, I want 2 plus 7i for them to actually be complex conjugates. Otherwise, I'm going to end up with a mess that was like the first example we did here. That's just a mess. We don't want that. Remember, whatever you do to the denominator, you must also do to the numerator. So we need to multiply both the numerator and the denominator. Now here's where it can get a little tricky. So if we break this down over here into mini steps, my numerator is 5 plus 6i multiplied by 2 plus 7i. So multiplying this out, I get 10 plus 47i minus 42. So 10 minus 42 is going to be negative 32. So I'll have negative 32 plus 47i divided by, now I need to multiply out the denominator. So I get 53 for the denominator. Now to finish this off, I'll have negative 32 over 53 plus 47i over 53. And I have no more i's in the denominator, which was what we wanted. All right, let's go ahead and do the second bit. So the first thing we're going to want to do is, again, multiply by the complex conjugate. So since it's a minus, I'm going to have 3 plus 5i in the denominator, 3 plus 5i in the numerator. Okay, multiplying out 8 plus 2i times 3 plus 5i. I'm going to get, let's see, 8 times 3 is 24. So I got 24 plus 46i minus 10. That's going to equal 14 plus 46i divided by 3 minus 5i times 3 plus 5i. So I'm going to do this work over here. All right, I got 34. So this is going to equal 14 over 34 plus 46i over 34. And I can simplify these fractions because 14 and 34 both go into 2. So this is going to equal 7 over 17 plus 23i over 17. All right, this concludes our 8th lecture of the semester. Thank y'all so much for tuning in, and I hope you have a wonderful rest of your day.